Can you hear me? I think seems like people have decided where to go. So we are starting this session now. And as Dan said before, after these sessions, you will be asked to vote for one of the presenters to go to the People's Choice panel by the end of the day. And of course, the reason for that is that we've got 3 parallel sessions going, and we want to kind of highlight the ones that you think the other teams would should see as well. We will have 15 minutes per talk, and just to short check, we've got Shiwen here today, got Anthony Rowe, is he here today? No. Jeff Andrews, so you will present, perfect. And then Deepak, Vasisht, perfect. So we got 3 presenters here today, meaning that we will have some time for questions afterwards. So my proposal is that we run 15 minutes presentations, and afterwards you get a few minutes for questions as well. When it's 5 minutes left, you'll be getting this one. 1 minute left, you'll be getting that one, and after that I will break. So then I welcome, how do you pronounce, Shiwen Mao to the stage to present the learning-based, resilient, immersive media compression, delivery, and interaction, which is a favorite of mine because I'm heading up the research area, digital representation and interaction in Ericsson, doing media compression and interaction. So welcome here, Shiwen.
Yeah, thanks for the introduction. So, so we want to thank NSF for funding us for this project. So it's a joint project with Shiwen Mao, that's myself, and with Auburn University, and Zhu Li, he's an expert on compression. He was UMKC. How do I use this? Oh. Okay. Okay, yeah. So the goal is to, so you see LRIM. So L means learning, RIM, then we have this resilient R immersive media. So basically we want to use, we want to use kind of new technologies in AI, machine learning, and also 5G, 6G next generation to support immersive user experience. Okay, so we have 5 thrusts. The first 2 are mostly focusing on deep learning-based compression of immersive media data, and we have focus on light field and also point cloud compression solutions, respectively. The third and the fourth are more like related to wireless networking side, focusing on gaining understanding on performance limits and understanding the systems, and also developing algorithms and schemes. And the last one is system integration validation. We also have a plan for outreach, dissemination, diversity, and etc. So some highlights of what we have accomplished so far. So we, in the last year, we tackled the problems on the first part is compression. So deep learning based algorithm schemes for compression and analytics of video and like point cloud and light field data, immersive media data. And also we tackled the transmission aspects of metaverse and digital twins, like how to schedule transmission to optimize this concept of age of information or age of synchronization, and how to develop auction techniques, schemes for resource allocation. And we also applied some recent advances in generative AI to address these problems. And some quick highlights. So Professor Zhu Li's team, they developed this AI-based dynamic point cloud geometry compression technique that has been adopted in MPAC. This PCC, point cloud compression test model. And last year, they participated in this CVPR. There was a PBVS workshop competition. They were ranked the top 1 U.S. team among U.S. teams. And this year, they participated in the competition again. They ranked the top 1 U.S. team and the top 2 among all the teams worldwide. It's like over 100. I think somewhere here. Yeah, 100 plus teams worldwide. And their model size comparing to the top 1 team is only like a 1/50th. It's very small, much smaller model size. Okay. And we also won a Best Demo Award at InfoComm 24 in May this year. And we already graduated 2 PhD students from the project. So next, in the next few slides, I will quickly go through 3 pieces of our work to give you a feel of our work. So the first part is mostly is denoising or is this model. So that is used to process this decoded point cloud to remove the artifacts. Okay, so because it's a lossy compression, so it's more like a post-process module connected to the output of this point cloud decoder, then give you a cleaner, better quality point cloud. Okay, so the idea is to use this. Let me see. It's a torch sparse based system, so that can handle very sparse tensors, okay, sparse point clouds. And so we will implement this and compare the performance with this MPEG kind of a standard component. There is a bit saving of up to like 13%, okay, comparing to this MPEG benchmark. And also it outperforms several state-of-art techniques. So the idea is to have this, so basically this is a decoded point cloud. You feed this into this TSF. It's a transformer space frequency, this decomposed feature fusion network. So we extend this to handle 3D point clouds. And then it has it downscale this point cloud data twice. So we can extract features using this RFB 3L modules at 3 different scales. And then it's a ResNet kind of structure. So you see this bypass kind of connections. So the extracted features are then fused by this transformer with self-attendance attention. Then eventually you get improved output. So that's basically that's the architecture. So we here are some results. So you can see here on average we can achieve like a 13% bit savings. Okay, bit rate savings comparing to this MPEG standard. And here are some visual effects examples. So this is a ground truth, and this is ground truth. And you see this is the MPEG result, and these are the results produced by this technique. It's about like a 0.5, around 0.5 dB gain. Okay. The second piece is more like a networking part kind of results. So we consider a metaverse, a mixed reality, okay, metaverse for vehicular, for autonomous driving. So yeah, it's here. So we have a metaverse, the virtual world, and we have the real world. So we they interact, and then through these 3 components, autonomous vehicles and roadside units and the virtual simulators. Okay, so we can apply this generative AI to synthesize different traffic scenarios and different traffic and the driving simulation scenarios, and for training and for interaction between the world in this mixed reality system. Okay, and And the problem is formulated as a non-cooperative game between these three components. So these AVs, RSUs, and the virtual simulators, and the goal is to maximize this social surplus. Okay, and we develop a auction-based second score auction-based mechanism called the MTP Visa, and we prove that it's a strategy proof and is fully strategy proof and is adverse selection free. And here is an example of this MR kind of scenario. So it's a driving in New York City, okay, kind of a scenario, and we can generate various kind of traffic signs to augment this reality and this virtual world and for training, okay, based on the user preference and catch the data, historical data. And here are some results for, we can make use of this metaverse kind of history and the data and for trajectory prediction. And I'm sorry, it's kind of a little blurred, but there are two colors, green and black. So basically, if you look at the R2 score, so the trajectory prediction results are quite accurate. And these are some results for this traffic sign generation. And we can generate different kind of traffic signs and also different recontextualization, different backgrounds and colors, etc. And this shows the results for the this mechanism, this auction mechanism. Yeah, almost. And you can see the social surplus, okay, achieved by this AIGC plus this auction mechanism give you the best result. Yeah, the last piece, the third piece is our recent work on generating how to use this AIGC to generate wireless data. So we know that wireless data are very dynamic, very difficult to collect. It costs a lot of labor and hardware. Okay, and also wireless data expands many dimensions, different spectrum like 900 megahertz RFID and the millimeter wave channels. Even in the same environment, you see very different kind of channels, different conditions, and different time, different space, different signal noise ratio, different protocols, hardware design, etc. So basically, it's very costly to get a rich set of data sets to train your machine learning models. Okay, so our idea is that we synthesize, okay, RF data. Okay, the target application is a 3D human pulse monitoring. So we shoot a wireless signal on human body, and by detecting this reflected signal, we can detect a human 3D pulse, okay, in action. And the idea is that to use this stable diffusion model, okay, that is a very recent machine learning model. So we first it includes two loops. The first is forward diffusion. So by starting from a valid wireless signal, by keep on adding noise step by step, then we destroy the signal to Gaussian noise. Okay. But during this process, we learn how the noises are generated. Okay. Then in the reverse diffusion direction, so we start with noise, then we keep on extracting, subtracting noise. This learned noise from this Gaussian noise. And eventually, we get a valid example. Okay, so that's the idea. Here is one example. So on the right-hand side is an image kind of example. So we start with white noise, then we keep on subtracting noises, then eventually we get a valid image. And this is an example for, the animation doesn't show, but this is an example for RFID data. So basically, start from white noise, we keep on subtracting noises. Eventually, we get a valid RFID example. Okay. The idea is very similar, but we showed that it works for wireless, not just for images. Okay, and we use this generated synthetic RF data to train a machine learning model for this human activity recognition classification. Like here is like 6 different type of activities. Then you can see that this is 88%, this is 81%. This 81% is obtained with 32 minutes of real data, and this 88% accuracy is obtained with 128 minutes of synthetic data. Well, the synthetic data come at no cost. You can just run the program to generate as much data as you want. Okay, so for future work, we will most be focusing on 2 directions. One is generative AI, AIGC. The other one is more recent, quite a new technique called Gaussian splatting. So we want, I'm done. So yeah, we will focus on these 2 technologies and to see how to apply them to address this immersive median or like a point cloud or light field data. Okay. And this is the team. So with that, I conclude my talk. I'll be happy to answer questions. Yeah. Yeah, that's a good question. We haven't tried that, but I think the key is that you want to learn how to generate those kind of noises, delta, small noises, by through the process of when you destroy this valid image or valid sample. Once you learn this how to generate these little noises, then you can go the reverse direction. Then you can to generate synthesize valid data. So that's the key idea. But we haven't tried other kind of noises distributions. Yeah. Thank you. Yes. Mm-hmm. Yeah. Yeah, I think they used the several standard test set. It's like they tried 6 different point clouds, and they used the training is using sorry, it slipped my mind. It's in the paper. So they used the one public standard test set, but which was mesh based kind of point clouds. Then they discretized the mesh into generate something like 1 million points per point cloud, and use that to train the model. Then they tested. The test results was on a different set of data set. Yeah. I can show you the paper offline. So yeah. Thank you. Thank you.
Very interesting. Yeah. So let's see. Continuing the program here. I think Anthony Rowe was not here unless he showed up. And then next here will be deep generative models for ultra high dimensional next generation communication system. And standing in for Jeff, we will have Tae-kun. So welcome.
Yeah. Thank you. Hello, my name is Tae-kun Lee, and I'm the lead PhD student of Professor Jeffrey Andrews and Professor Alex Demakis. And I'm going to talk about deep generative models for ultra high dimensional next generation communication systems. And in this presentation, we'll specifically look into this the work using diffusion model to capture the channel distribution. How can I go to the next slide? Oh, I see. I think it went back. Yep, I see. Yeah, so there are a lot of deep learning use cases in wireless communication. So as you can see here, such as channel compression, and also the second one is a little bit complicated, but like single user MIMO scheme for joint CSI acquisition and pre-coding and site-specific beamforming. These will be talked about it later also. So the deep learning based method is already used in already like being a research area in wireless communication. And the one specific characteristic is that they are highly dependent on the data set that we train on. So the motivation of the work is that the advancements in deep neural network has led to the developments in millimeter wave wireless communication, especially like deep neural network based pre-coding and also beam tracking and those kind of use cases. But the deep learning based methods require a large amount of training data, such as like in macro cell sector, we need about like 100K channel measurements, and this is kind of prohibitive to collect and train the model. So it might be impractical to obtain from the real world environment to do this. So there are lots of like alternative solutions like using digital twins or those kind of thing. And maybe this can be the work to suggest another way to obtain the amount of data set. Yeah, so just directly going into the details of the work, this is the high level illustration of the proposed method. Actually, yeah, it should have been PDF. But so the first thing to do is to collect the channel matrices and then the UE positions of the data set. And what we do is to train the diffusion model by denoising the noise added channels conditioned on the position of the channel. And then we boost the data set by new UE positions that were not in the training data set as a conditional input to the diffusion model. And then finally, we use this data set offline to train the downstream tasks that are using deep learning. So the augmented data set contains much more than the training data set, and then they can be used into the various different wireless communication problems. Yeah, so the key accomplishment is that like this is, as all we know, this is the first method to generate the user-specific channels at precise locations. And also this method leverages the diffusion model, and this can kind of do the non-trivial interpolations and extrapolations based on the limited training data. And we validate our synthetic channels not only looking at the NMSC or something like that, but also evaluating to the wireless downstream tasks also to see that if it is a valid data set. Yeah, so for the related works, there were lots of trials to do the data augmentation. So first, like something like using the CNNs to capture the channel statistics have been tried, and GANs, generative adversarial networks, were also used to learn the channel distributions, and also there were trials of making channels from the diffusion model also, and our work is kind of trying to capture the direct relationship between the channel matrix and the positional information to generate the augmented data set. Yeah, so the what the model that we use is conditional DDIM, and DDIM is one of the models in the diffusion model. So what we want to do is kind of using the latent vectors to generate the channel. So this is kind of the previous work that were done in human face. So as you can see there's a semantic encoder. So if we put the image as an input, then the semantic encoder makes the latent vector. And that latent vector is given as the conditional input. And then in the diffusion model, it starts from the Gaussian noise. And then the noise is denoised step by step to make the human face. So this latent vector that is from the semantic encoder is actually having the information of the human face. So the image can be reconstructed. And as you can see here, like if we change some parameters, like we can change this to the young face to older face or something like that. So in our case, this becomes a little bit different. Like it's easier to understand. So instead of putting the latent vector, we're directly putting the user's position information there. So it just goes into the conditional input, just like that latent vector, to generate the channel matrices to boost the data set. Yeah, so the system model is like this. A narrowband massive MIMO system is considered, and we use the Quadriga and DMIMO datasets in this experiment to do the simulation. And our key insight is that, like, when doing the experiments, we just found out that beam space representation channel could be captured by the diffusion model. So we looked at the channel in the beam space representation. Yeah, and this is the proposed deep learning model. So this is conditional denoising diffusion implicit model. So the architecture is using the UNet. And each of the residual convolutional block is consisted of sequential convolutional layer, batch norm, and GALU layer. And then those blocks are consisted as a UNet structure. So as you can see there, there are like hierarchies of the layers. And then the input, the UE position input is given as a conditional input. And then the Gaussian noise is denoised n times to finally output the synthetic channel. So the model inference is done assuming that the diffusion model is trained. This channel sample is generated from the random noise channel and a specific user position. Yeah, and this is the simulation setup. So we use two different simulators to do the experiments. First is Quadriga, and second is DMIMO simulator. So the channel generation process is like this. So first we randomly locate users within 100 meters of the base station. And secondly, we generate the initial channels at 28 gigahertz. And then thirdly, we use diffusion models to create the boosted amount of the channels. And then lastly, we evaluate the performance in the downstream tasks and visualize the channels. Yeah, so when we look at the channels and see if the generated data is realistic as real data, in our scenario, we found out that the middle row is, middle column is from the diffusion model, and the right column is the reference column, and the left column is from the GAN. So as you can see there, like the LOS peak is not captured when we use GAN, but LOS peak is captured when we use the diffusion model. So we also quantitatively compare our method with the channels that are generated from the diffusion model with choosing the closest UE in the training data set. And we found out that when even we choose the channel that is the closest in the training data set, we cannot beat the case when we use the diffusion model. So this means that we're doing the right interpolation when we use a diffusion model to boost the data set. And actually, like when we use GAN, it wasn't able to generate the reasonable peaks. So this means that like the channel that is generated from the GAN is not capturing the distribution very well. Yeah, and also there was additional trials of step reduction. So currently, the biggest problem of the diffusion model is that it takes a lot of time. So we tried two approaches to decrease the inference complexity. So first is progressive distillation, and second is consistency models. And actually, these two were having some some limitations of the performance, and this is because of the lack of the training data set. Not like the diffusion model works in the computer vision or those kind of areas. So this means that we need more and more data to train the channel-based diffusion model. Yeah, and these are the results of the downstream tasks, and I'll just explain briefly because of the time. So first is channel compression, second is joint CSI acquisition and pre-coding, and third is site-specific beamforming. Yeah, and in channel compression, as you can see here, when we use the diffusion model, the NMSC value is stick to the lowest level. So this means that our diffusion model is giving the best NMSC performance. And secondly, joint CSI acquisition and pre-coding. This is not doing the channel estimation, but directly pre-coding based on the pilots that we receive. And the result is that our method shows the highest capacity. So when we use diffusion model, the channel generated is giving the best pilots that are optimized. And also for the site-specific beam alignment engine. So this is learning the site-specific probing beams. And when we want to train this module, we need the training data. And those training data are from the boosted data set that are from the diffusion model. So in this case, we can also see that our method shows the highest SNR, even beating the exhaustive search. So this means that our learned grid-free probing beams are showing much better result than just the DFT probing beams. And all the other synthetic data that are generated from the different methodologies are not giving high enough SNR. So this means that the learned beams are crashed. So the augmented data set is not doing the right distribution capturing. Yeah, so for all of these results, maybe we can discuss more in the poster session when we do the poster session. Yeah, so for the challenges and future work, so our novel framework for augmenting the data set using a conditional diffusion model is as shown, can be applied to the diverse downstream tasks also. And future research could be looking at the extensive inference time, and also considering of the specific characteristics of the millimeter wave channel matrices. So such as the things that we consider as progressive distillation and consistency models, which to reduce the time, and also applying some recent methods to inference from the partial information that we have also. Yeah. Thank you. Yeah, finished.
Oh, you finished.
Yeah.
So, thank you, Tycoon. Do we have any more questions or any questions? We have a few minutes. Yes.
Oh yeah, thank you. So the baselines that I've compared with is first, if you have the small amount of the channel data, we can just add Gaussian noise to boost the data set, and that's the adding noise. And also, if you use generative adversarial network GAN to capture the distribution, then we can put the different latent vectors inside to generate the augmented data set. Yeah, so those two are the baselines. Yes. 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 So there's a single user, and there's a single transmitter, and there's a single link, and we just look at the average SNR of that single link. Yeah, in the last graph that you said. Yes, yes. Yeah, there's no special multiplexing, just the like beamforming. Yes, yes. Yes.
Thank you. One short question.
Yes.
Can you think of a dots where the realism of your stated data good enough?
Oh, still not good enough? That's a good question. Actually, I think that there still is a lot of limitations because actually we're not having the like exact simulation details, but like just using the single model to capture all the channel distribution. So maybe if it becomes more and more site specific, for instance, like if there's a like tall building or something like that, then maybe it will be harder and harder to capture itself, I think. Yeah.
Okay, thanks. Thanks, Tycoon. So moving on to next presentation here, we will have Deepak presenting Provably robust machine learning for next generation cellular networks. Welcome.
Hey everyone, I'm Deepak. I'm going to talk about provably robust machine learning for next generation cellular networks. This is joint work with my co-PIs Gagandeep and Romit, and also like a lot of the students who work on this. So yeah, this session we've seen a lot of machine learning use cases. We know machine learning is a really powerful tool for wireless networks. And there are multiple like potential applications that we see, both in academia and in industry, and both for communication and for sensing. You'll get to hear a lot of them today. Like we ourselves have looked at applications like channel prediction across frequency bands in FTD systems, localization and sensing, and there's a lot of other people who have looked at this in academia, multiple papers in top conferences. I'll not go into details of like why machine learning is so useful. I guess we already kind of believe at this point in that thesis, and there'll be a lot of talks, like we've seen talks before, and we'll have talks later. And clearly, one advantage of machine learning systems is that they can learn about the environment and provide better performance in whatever metrics we care about for either sensing, localization, positioning, communication. But the question that I want to ask today is that is performance enough, right? Because in wireless systems, we have to actually deploy these systems in the real world. And we also care about reliability, right? That we want these systems to be reliable when they're deployed in the real world. And that's the thrust of our work. So we have three big themes in our project. The first theme is building new machine learning techniques that are leveraging the knowledge that we've gained from signal processing approaches to build models and demonstrate state-of-the-art performance in multiple problems. So for example, we've worked on machine learning-driven channel prediction across frequency bands. We've done a bunch of work in wireless sensing using machine learning in the last couple of years in this project. So one demo that you see here is using millimeter wave to perform SLAM using robots. The second thrust of our work is on reliability, that when we take these systems and deploy them in the real world, what kind of vulnerabilities do these systems have? What kind of challenges do these systems face? And to this end, we demonstrated the first real-world adversarial attacks against machine learning systems. These are neural networks-based systems for both communication and sensing. This work was done as part of our RINGS project and won the Qualcomm Innovation Fellowship, I guess, last year or so. And then once we've exposed these kind of vulnerabilities, the next step obviously is that what can we do about it, right? How can we design systems that are more robust in the real world? So to that end, we have done a lot of theoretical work in establishing robustness guarantees for these systems in terms of when they get deployed in the real world. And the next step that we have is to demonstrate this in practical wireless systems, which is what we'll focus on over the next year. So as you can see, these are the three kind of major things that we've been focusing on. We only have 15 minutes, so I'll not talk about all of them. I'll focus on the middle piece here today and give you some insights into what are the unique challenges for reliability in wireless systems, right? So we've seen work in other domains. So why is wireless as a domain different? And what can we do to address these kind of challenges that arise that are specific to wireless? Okay, so it's not no news that machine learning systems are vulnerable to attacks. And a classical example is that if I take a machine learning model and give it an image of a panda, it can very easily classify this as a panda. But I can also craft very carefully crafted small amounts of noise and add it to this image, such that this image still looks like a panda to you and me. But if I give it to the neural network, it'll think it's a dog or a cat. This is this domain called adversarial attacks on wireless systems, and a lot of work, adversarial attack in vision domains, and a lot of work has focused on these kind of attacks. Now the question is, what if we can do this in wireless systems as well? And that can have pretty disastrous consequences, right? Because wireless systems are critical infrastructure today. They provide a lot of critical services. And if I can do that, it can be pretty dangerous. So imagine that I have a base station that's deploying machine learning to provide both, say, communication and positioning services. And it's using machine learning to do that. If an adversary can inject very, very small amounts of noise that's potentially undetectable by the base station, it can cause this device to have a very wrong sense of its position. So it can have several meters of error or tens of meters of error just by injecting small amounts of noise that is indetectable in these systems. And if you're deploying these systems for critical applications like self-driving cars or autonomous vehicles, it can potentially move you from one lane to the other, causing crashes. You can imagine similar attacks on communication services as well, which has consequences leading from being annoyed that my TikTok does not load to actually like really critical services like remote surgery. So it is very important to study how robust and reliable these networks are before we actually go ahead and deploy them. So our work built the first RF systems-based attack in the real world. The highlights are that this is the first real-world attack on machine learning-based wireless systems, works for both communication and sensing. We can administer these attacks without any coordination with the base station, no synchronization required. It's completely independent of the base station or the client, does not require any software or hardware changes. We also perform a hardware-driven evaluation in the real world against some of these systems. And we've shown some early work, as I said, on defense strategies. We're still building more. And again, the point of this is not to show that, not to attack these systems, but to expose what kind of vulnerabilities exist so we can address them before we actually go ahead and deploy them. Okay, so let me give you a little bit of detail in this attack, and then I'll kind of like pop up the stack and give you some brief takeaways at the end. So the setup is the following, right? So in machine learning, as you know, there's a training stage where you take a bunch of training data and you train a neural network, and then there's a test stage where you give it new images, for example, and the neural network will predict what this image is. Right? So in the wireless case, it's kind of similar, that in the training stage, you take some wireless signals, say the wireless channel, you have some output, say location, modulation, or so on and so forth. And then you train a neural network to take these signals and predict the modulation or the location. And at the test stage, you take a new signal and you want the output. So the attacks that we're considering are test time attacks. So we don't assume that we have access to the training data at all. Like the base station has a model that it has already learned, is deployed in production, and at test time, we introduce small amounts of noise to cause these errors in the systems for any of these like systems that we care about. And the goals of the attacker are to be realistic, right? So we want this to be a realistic system. We want it to be coordination-free, that the client should not, or the adversary should not assume any kind of coordination with the base station. It has to be low power because if you introduce high powers of noise, of course, you can jam any system. The idea is to show that you have like very, very small amounts of power that are undetectable and still cause errors in machine learning systems. And these errors should be much larger than what you would anticipate with, say, Gaussian noise in a traditional system, right? Like otherwise, it does not like really show the vulnerability of the wireless system. And we want it to be low complexity. We don't want the overhead on the attacker to be high so that we show some kind of like universal attacks. So traditionally, when you design these wireless systems, the way this works is the following. So you have some input to the network, let's say H, which is the wireless channel. You add some noise. You pass this through the network, and you compute the loss. And then instead of doing gradient descent to minimize the loss, you're trying to do gradient ascent so that your loss keeps going up with the small amount of noise, with some bounds on the noise. And then you keep updating your noise till you find a noise that works for that specific input. Now, this is how like this is done in the vision community in general. So it has two key requirements. One is that you need to design a noise that is very specific to the input that you have for the model, which is H. So you need to know what the input is. And you need to be able to add this n. So you do a lot of work to precisely compute what this noise is so that when you add it, it causes the exact amount of damage that you want. Unfortunately, in wireless systems, like both of these conditions are not true, right? We don't know what the communication between the client and the base station is, what channel is being used, because the channel is very specific to a location. If you're not at the same location, you don't have coordination with the base station, you don't know that. And you also cannot add the exact amount of noise that you want because, you know, like noise has its own, like the noise that you add will also go through a channel, will have like carrier frequency offsets, clock offsets, timing offsets. So you have to deal with all of that. So these are the challenges that are specific to wireless networks. As I said, the attacker does not know the exact value of the channel. And as a result, it has to kind of like find a way to get around that. So can we design a noise vector without knowing this channel between the client and the base station? And to do that, we have an idea. Okay, it's kind of simple. Why don't we design a noise vector that works for multiple possible values of H or the entire distribution of channels in a given space so that you don't have to care about what this channel is. And to do that, we can modify this pipeline over here in a very simple way. So instead of having an N work for a given H, we have it work for H that is sampled from the environment at runtime. So you learn to design noise vectors that will work broadly for a class of H as opposed to just one value of H. So this thing is called a universal adversarial perturbation. Adversarial because we want to cause errors. Universal because we want it to work for all possible values of H. Okay, so as I said, the second problem here is that even if I do this and design a value of n, the noise itself will get distorted by the wireless channel itself, mostly because of two reasons. One, that there is a channel that the attacker experiences themselves, that the channel will cause distortions to the noise. So the noise that you design and the noise that gets added are very different. And the second reason is clock offsets, right? So you will have no synchronization with the base station or the client. And in this case, when you transmit your noise, it's not synchronized in time, leading to offsets. So if you want to, like ideally you want to align noise with your preamble, for example, if you want to cause errors in the channel, but you will have like offsets. So yeah, in the interest of time, I'll not talk about like what all these channels, what all these noises are, because they're we just model them specifically because we know what they can be, and to do that, we want to design noise that is robust to these kind of effects. So we designed this new technique called I'll skip this. So we designed this new technique called robust adversarial. Sorry, I'll just go here. Yeah, so we designed this new technique called robust wireless UAP. So this is robust to all these wireless transformations. It is universal, it is adversarial, and it's a perturbation. And to do that, all we do is that we introduce these factors in the noise training process itself. That is a bunch of transformations that we can apply to the noise during the training process, so that we figure out a noise that's averse to these kind of transformations that I talked about. Okay, so just show you quickly some results and how we can avoid this as well. Just to talk about that a little bit. So our attacker is fairly simple. Like it's a single antenna attacker. It has 20 dB less power than the client, or at least 20 dB less power than the client. It can have like even lower power. And the attacker does not have a lot of capabilities. As you can see, it has a single antenna, does not use multiple antennas and stuff. And this is deployed in an indoor environment. It's an indoor lab space, different position of the client. The attacker is at a fixed location, not at the same location as the base station. And you can see the environment is pretty diverse. The base station is running machine learning models for both communication and sensing. I'll show you one result for communication, and then maybe we can talk later in the poster session for more results. So this is where we are attacking a system called FIRE, where the input is a wireless channel, the output is a wireless channel on another frequency. It's a neural network that does this prediction. So this system achieves a channel SNR of about 17 dB in this environment. And when we attack this, the performance goes lower, actually significantly lower. So the average performance is about 10 dB. So you get 7 to 8 dB loss with like very small amounts of noise. And this is because this noise is carefully crafted. And in 20% of the cases, the noise is even like much larger, like like you go down to about 5 dB in performance. So the question is, how can we use these insights to build more robust models? And what we want to do is we want to inject these systems or use like our system called RAFA to improve the training process. So typically the training process looks like this. You build a machine learning model through training, and then you deploy it in the real world. And when you deploy it in the real world, you find these problems, right? We want to find these problems before you deploy it in the real world. So during the training process itself, we want to ask questions that, is this a trustworthy model by using this adversarial attack? And if it is not, then we want to update the training. Okay? So we did a bit of that already. So the idea is that we show this machine learning model examples generated by RAFA that are adversarial and see if it can improve the performance. And we see that this robust training can improve the performance by a little bit. There are two challenges that still remain. One is that there's still no guarantee, right? That maybe this attack is robust to this attack, but maybe other kinds of attack it can still not be robust to. So we want provable guarantees. And we also want this system to be like easy to train and not have as much loss in performance even under attack. So that's our next step. So to conclude, machine learning systems are very useful. They underline many performance benefits at the physical layer in wireless. However, robustness of these machine learning models is not guaranteed. There are new challenges when you deploy these systems in terms of vulnerabilities and attacks. And hopefully, the certified robustness systems that we're developing can improve trust in these deployments as we move forward with them. Yeah, that's my time. Thanks a lot, and I'm happy to take questions.
So thank you, Deepak, and we still have time for questions. And while you answer the questions, I will go out handing out these index cards to get a chance to vote who should go on the people's panel for the end of the day. So which of these presentations do you want to see for the others that are in the other rooms now? And we got Shiwen, and we got Taekun, and we got Deepak that you could vote for. So I'll let you take the questions while I hand this out.
Go ahead, yeah.
So you focused on the robust. Why didn't you focus on?
Yeah, that's a great question. So just to repeat the question for online audience, the question is that you focus on robustness, but this piece does not talk about explainability. So we do actually have some work on explainability. It's just that I did not focus on it today. And I guess the high-level gist of the explainability question is that I think we need to learn from how traditional signal processing methods work and use them in conjunction with machine learning to be able to explain stuff. But yeah, I guess maybe that's a more detailed question, so we can take it in the poster session. But we do have some work in that space. Just did not focus on it today. Yeah. Yeah, go ahead.
Makes sense.
Sure.
Given that the noise that you're introducing is not done, does it make sense to
Yeah, that's a good question. So the question is that, hey, the noise that you're introducing is not Gaussian. Does it make sense to use SNR as a metric? Yeah, so I think that's a good question. So typically when we are actually designing this robust noise, the current version of the algorithm uses essentially a threshold on the max of each subcarrier to be within like at least less than 20 dB of the average SNR. But there is a way to kind of mimic distribution. So if you want it to be like, let's say, within some difference within some difference from Gaussian noise, we can do that. And I guess the errors are slightly lower, but not that different. That I guess still quite effective. Yeah.
Then maybe we should break up or do one more question. Okay, thank you, Deepak.
Thank you.
So this was the end of this session, and the next session will start at 11 o'clock, and let's try to be in the right room starting 11 sharp so we get time for questions in the upcoming presentation as well. The index card, yes, you can come and drop them off here in front or give them to me. Thank you.